Hello, I'm Johnny, and today I'm presenting Guardride, an AI-powered safety companion for e-scooters and e-bikes. Guardride uses sensors and AI to monitor helmets, fatigue, speed, and collision risks in real time. Our goal is simple: make micromobility safer and more trusted. Before I get into my project, we first have to understand why it's necessary. Starting from around 2017, micromobility has exploded in popularity, but safety hasn't kept pace. Between 2017 and 2022, in just 5 years, over 360,000 people have ended up in the ER from e-scooter accidents. And when you look at that 360,000 graphed out between the 5 years, you can see the steady incline, with the only plateau happening during COVID between 2019 and 2020. Current safety tools and measures are reactive. Helmets and padding only help after a crash, but they don't help prevent one. There's a big hole for active safety measures in the micromobility industry, so that's where Guardride comes in. Guardride is an AI-powered safety system that monitors speed, helmet use, fatigue, and collision risk. It also includes a mobile app interface. So here's a sort of close-up look at Guardride's design. The main base is in its case, but the sensors and cameras are not. They're not mounted. When the case is fully on, they would all be screwed in and mounted, but this look is just so you can see all the main hardware pieces. To be more specific, at the core of the Guardride prototype is a Raspberry Pi, which is the processing hub, and it also includes a screen, which you can see in the diagram. The Pi is connected to a motion and distance sensors, which are the IMU and TOF sensors, and it also includes a camera. All this data that the sensors and camera give is processed in real time, and alerts are delivered directly to the rider through a small touch screen, which the screen is also pointed out in the diagram, or through the app. The companion app also runs its own fatigue and helmet detection through the phone's camera, which extends the safety coverage of Guardride. The IMU sensor in Guardride senses sudden tilts and decelerations. In our tests, it detected 18 out of 20 simulated crashes, or about 90% accuracy. But Guardride doesn't just stop at detection. Once a crash is confirmed, it immediately notifies the rider and also sends an alert to a pre-selected contact. This could be a parent or a friend. This way, someone else knows if a rider goes down and can respond quickly. The TOF sensor measures how close riders are to objects in their path. It sends out a beam of light and measures how long it takes for that light to bounce back, which tells us how far away an object is. If something is too close, Guardride warns the rider. This is especially useful in a crowded city environments where scooters are most popular and they share space with pedestrians, parked cars, and street furniture. The TOF sensor is simple but effective because it constantly gives us distance information that riders themselves may not notice until it's too late. Guardride also includes a camera that adds another layer of collision avoidance. Unlike the TOF, which only measures directly ahead, the camera has a wider field of view. This means it can pick up obstacles like poles, curbs, or even overhead objects that the TOF sensors might miss. The visual input also makes Guardride more adaptable, since it can handle varied conditions that distance sensing alone can't capture. Together, the TOF and camera give readers a much fuller awareness of their environment, which helps prevent accidents. The IMU also gives Guardride the ability to monitor speed. By tracking acceleration and integrating it over time, we can calculate velocity and display it in both miles per hour and kilometers per hour. If a rider exceeds a limit, Guardride provides a warning in real time. The alert is designed to grab attention without startling the rider, keeping them informed and aware. For younger riders in particular, whose parents will give them Guardride in hopes to protect them, an alert will be sent to their parents whenever speeding occurs. So this is an example of what the display on the device would look like during a drive, with the display on the left and a close-up of the screen on the right. So on the left, you can see it shows the speed the rider is moving at. They get a pick between miles per hour and kilometers per hour. And then below that is a slider that goes from green to red. As the slider moves closer to the red side, it means the object detected is getting closer and closer, becoming more dangerous, which alerts the driver to become more aware of what they're going to do next. Alright, so this is our current hardware prototype. It works, but we see several areas for improvement. First, the casing right now is basic and it's just not the best. Our goal is to design a stronger, more durable case that protects the electronics, but also remains lightweight and compact. Uh, Lots of the e-scooter and micromobility riders only ride the vehicle for around 10 minutes to 20 minutes, and it becomes extremely inconvenient to have to carry something bulky around. So the goal is to keep the device small enough as to where it can fit in your pocket. Secondly, we want to explore alternative component options to make manufacturing cheaper without sacrificing quality. And third, we're finalizing the attachment system that lets the unit securely connect to scooters. As of right now, we have an attachment system that connects to handlebars. However, it's not the easiest to mount and it's not extremely stable during rides. So that's something we're looking for. We're gonna try and improve on. Finally, we plan to make the overall design smaller and more compact, so it feels less like a bulky add-on and more like a sleek piece of equipment riders would actually want to use. So moving on to the role of the app serves as the rider's interface, the place where alerts and speed data are displayed clearly along with the screen. The app also adds fatigue and helmet detection, something that the hardware itself doesn't cover. By combining both, we make Guardride more versatile, and the rider gets real-time feedback from the hardware and additional insights from the app. So here are some example screens from the app. The interface is deliberately clean and simple, and on the main screen, which is on the left, is the screen the rider sees as they ride, the rider sees the speedometer, helmet status, and fatigue alerts. The design avoids clutter and distractions because the last thing we want is for riders to be fiddling with their phones while moving. By making the user interface minimal, we give riders the information they need at a glance without pulling attention away from the road. So, fatigue is actually one of the hidden dangers of micromobility, with its contributions to over contributing to over 30% of accidents. To combat this, we developed an AI to detect how tired the user is by searching for signs that indicate weariness. If it detects fatigue, the app automatically sends an alert to the user suggesting the rider take a break. And if the rider just chooses to continue riding, as taking a break is not always a viable decision, it'll instead lower the speed limit for the rider. Along with fatigue detection, we also developed an AI to detect whether or not the user is wearing a helmet. If it doesn't detect one, the system automatically caps the max speed. This is a smart way to encourage responsible habits without forcing compliance. The user can still ride without a helmet. However, as a helmet will make the user safer if they crash, lowering the speed helps encourage the rider to continue to wear helmets, as the rider will quickly realize that wearing a helmet gives them full access to their scooter's speed, while skipping the helmet slows them down. It's a built-in incentive that improves safety for everyone. So here's a look at some of the code behind the app. This snippet was written in Flutter, and it creates a toggle for fatigue detection. So when enabled, the app continuously monitors the rider's face and provides alerts when needed. And when it disables, it pauses detection. This balance gives riders some autonomy over the system while still keeping safety at the forefront. The balance gives riders if active, it uses a conditional text widget that checks the Boolean variable is tired. If the value is true, it displays the message, you look tired, get some rest, and bold light colored text. If tired is false, it displays an empty screen hiding the message. And this alert updates automatically based on real-time AI fatigue analysis performed in the app. On the hardware side for some coding, this is a sample of the Python code that runs on the Raspberry Pi. The script reads input from the IMU, the time of flight sensor, and the camera roughly every 25 milliseconds. And this fast refresh rate ensures that the rider receives warnings almost instantly. For example, if the IMU detects a fall pattern or the TOF sensor senses a close obstacle, the system can immediately trigger an alert. As for one of our experiments, which was fatigue detection under different circumstances, when we tested fatigue detection, the system showed strong performance in distinguishing clearly drowsy users with a 95% accuracy rate for the very tired category. However, its accuracy dropped to 75% when users were only mildly fatigued, likely due to subtle facial expressions and borderline behavior. The not tired group was identified correctly in 90% of cases, though two false positives occurred, suggesting that the model occasionally overinterpreted temporary expressions like blinking or glancing down. These results indicate that the system is most effective when fatigue systems are obvious, but it may need fine-tuning for more subtle cases. Lighting and camera angles had noticeable impacts, with dim conditions reducing accuracy. Another one of the tests we did was testing our crash detection, in which we simulated falls by dropping or sharply tilting scooters with Guardride mounted. So the system correctly detected 18 out of 20 of the simulated crashes, resulting in a 90% true positive rate. Most of the missed detections occurred when crashes happened slowly or involved primarily rotation without a strong acceleration spike. This suggests the threshold for vertical and lateral acceleration might need further tuning. During non-crash scenarios such as curb bumps or sudden stops, the system triggered 3 false positives out of the 20 trials we had. These alerts happened primarily due to abrupt deceleration, which can resemble the early phases of a fall. While not perfect, these results are promising. The system is already able to distinguish most real crashes from normal riding bumps, and further fine-tuning will only improve accuracy. A major challenge for Guardride was integrating the parts into a compact, user-friendly design. We must consider how to fit the speed, fatigue, and proximity sensors into a form factor that does not interfere with the rider's experience on and off their vehicles while maintaining low production costs. If the hardware is too bulky, it would be inefficient to carry around the cities when riders use them and discourage use. If it is too compact and may not capture accurate data. To address these challenges, we could use miniaturized and low-powered sensors and design a system that can easily be attached to handlebars with careful component sourcing and efficient designs, helping balance cost and portability. Another challenge is the user experience. Guardride needs to deliver real-time alerts to riders about speeding, fatigue, or collision risks without distracting them while riding. A challenge is designing alerts that quickly capture the attention of the rider but do not cause panic or additional hazards. For example, loud alarms or flashing lights would startle riders, while subtle notifications might go unnoticed. To address this, we designed clear visual cues to appear on both the app and the device screen that ensure riders receive and respond to safety alerts effectively while maintaining control of the scooter. Looking forward, there are several key improvements on our roadmap. One is a more compact design to make Guardride easier to carry for riders, as we have already talked about, and the other is a better case design. We're also refining our algorithms to reduce the false alarms and enhance our AI detection for both helmet and fatigue. All of these improvements move us closer to a more reliable and scalable system. Guardride's mission is simple, to provide safety that rides with you. By combining hardware, AI, and thoughtful design, we can prevent accidents before they happen. Thank you for listening, and I'm excited to take your questions. All right.
Thank you, Mr. Johnny. It was nice presentation.